Winter 2015 question 11 QP11. The diagram shows part of the curve y is equal to 1 plus 2x to the power half and a point P 65 lying on the curve. The line PQ intersects the x-axis at Q 80. The III, we want to find, showing all necessary working, the exact volume of revolution obtained when the shaded region is rotated 360 degrees about the x-axis. For the winter 2015, the first question, as was shown on the screen, QP11, the first variant, and question 11. You had this diagram being shown there. I just tried to reproduce it in a way that will make it easier for you to see. So the equation of the curve y is equal to 1 plus 4x all to the power half. You see that? And we are saying that we have a normal to the curve at point P. So that normal to the curve at point P cuts the x-axis at the point 8 and 0. And it also cuts the x-axis, it also cuts the curve at the point 6 and 5. That's what we have been told there. Now, the problem is requiring us, our focus on the IR part is requiring us to find the volume of revolution obtained when the shaded region is rotated 360 about the x-axis. So guys, like we said in the earlier part and also on the video, and I'll encourage you, go to our website at learnwestafrica.com and take the revision course on calculus and integration. I'm sure you'll get a lot of practical examples to also get there. You can also subscribe and also take the one-on-one course that is also available with the instructor, and all that is also available on the website, so that you can have a clear understanding of all that we are speaking about. But essentially, like we know, when we want to find the volume that is created about the x-axis, it's more like how we would want to find the area under the area of the shaded part. So this area, it's what the same concept of trying to find the area, we would apply same in trying to identify what the volume is. So what do? Okay, now it should be clear to us that we can put this into two distinct parts. We can have that side. You see, look at the diagram carefully. So we can find the volume that will be created by the curve from this point to that point. And remember, because the x component of that is 6, we can find the volume that will be created by the curve from point 0 to 6. Okay, then we'll find the volume that will also be created by the remaining triangle from point 6 to point 8. So when you put the volume that will be created by the curve from 0 to 6, and also add up the volume that will be created by the normal, okay, from 6 to 8, the combined effect of that will be the volume that will be generated for the entire shaded region. Hope you understand the approach. All right, so now let's go and look for the volume that will be created on this side by the curve from 0 to 6. Okay, so how do we do that? Okay, it should be very apparent to us that we want to find the volume of that. Okay, we want to find the volume. That volume, okay, is going to be pi, then an integral of 0 to 6. 0 becomes your lower limit. That's where you are starting to your upper limit. So 0 to 6. And the equation of the curve is 1 plus 4x raised to the power half dx. Now remember, this is a linear factor, okay? We say linear factor because, remember, linear factor because what is within the bracket, the highest exponent of the x is 1. Okay, anytime you have an integral where the expression is such that the highest exponent of the x within the bracket is 1, we say that it has a linear factor. And we've mentioned that linear factors have got a very simple but special way of integration. Just add 1 to it. So we're going to have 1 plus 4x raised to the power half plus half plus 1, okay, half plus 1. Okay, then we divide this half plus 1. No, let's correct that aspect. Let's correct that aspect. When you have the volume 1 plus 4x raised to the power half, which is the equation, remember we have to square because we want the volume. Yes, we have to square. So this part will take a square. All right, so when you take the square away, what is going to happen is that this part will be left with 1. Okay, so that's what we are actually going to do. A square of that is going to give you like 1. Okay, so the exponent is actually 1. You just add, there's 1 plus 1 all over, okay, 1 plus 1 times 4. All right, so we are going to have 1 plus 4x all squared 1 plus 1 is 2 all over 8, okay? So we find that with the upper limit and lower limit 6 and 8 respectively. Hope you are fine. Okay, so let's take it again. 1 plus 4x raised to the power half, because the volume we square, and the square will take away the half to give you 1. Still for a linear factor, you add 1 to it, so you're going to have 1 plus 1 all over 1 plus 1 times the derivative of what is in the bracket. That's going to give you 4. So you put that up, 2 times 4 is going to give you 8. So this is what you do, and you attach the pi to it. Now, when you're able to do that nicely in there, you should get 78 pi. All right, so what it means is that the volume of the curve from 0 to 6, when it is revolved, 360 is going to give us 78 over pi. We are now left with one part, which is, what is the volume that will be created by that? The volume that will be created by this part, the normal there. What happens? Now, this is a straight line. Okay, so for a straight line, we need to find the equation of the straight line. How do you find the equation of a straight line? Pretty simple. Gradient plus 1 point. So we've already done that in our coordinate geometry lesson, so we didn't take so much time on it. You can also look at the text that accompanies this video, and you'll see how we're able to arrive at the equation of the line. But we'll simply just re-quote the equation of the line after going through the simple process to be y equals negative 5 over 2x plus 20, all right? So the equation of the line PQ is going to give you minus 5 over 2x plus 20. So now the question is, what is the volume that will be generated if we were to do that? Okay, so same, we will integrate. This time we are starting from 6 to 8. Okay, so we are going to start from 6 to 8. Okay, of minus 5 over 2x plus 20 dx. Then we'll square that 2. We add our pi. All right, we add our pi to that. All right, so if you're able to do that integration, which is a very pretty simple one, your volume, okay, your volume on that side is going to give you 50 pi over 3 square units. 50 pi over 3 cubic units, yes. Volume is cubic, okay? So just take a look at that. You find the equation of the straight line. You know the gradient, y2 minus y1 all over x2 minus x1, like we know for normal coordinate geometry. After all, choose the 1 point formula, y minus y1 equal to m into brackets x minus x1. That should produce the equation of the straight line PQ, being y is equal to minus 5 over 2x plus 20. Please make sure you take your time and work that to confirm that that's the equation of the straight line. Okay, so you integrate from 6, which is our lower limit, to 8, which is our upper limit. You square with your pi. So your volume is going to give you 50 pi over 3 cubic units. Hope you are fine. Okay, so now what is going to be the volume of the shaded unit? Because we said the volume of the shaded unit is going to be that by the curve and that by the straight line. You put 78 pi plus 50 pi over 3 together, and that should leave you with 284 over 3 pi cubic units. Okay, so that is the volume that will be generated from the shaded region if it is revolved 360. And that's it for question 11 of QP11. Okay? Question 9, QP13, winter 2015. A curve passes through the point A, 4, 6, and it is such that the y dx is equal to 1 plus 2x to the power minus half. A point P is moving along the curve in such a way that the x-coordinate of P is increasing at a constant rate of 3 units per minute. Find the equation of the curve. All right, so for question 9, QP13 of winter 2015, our focus is on the II part, okay? The II part where we are told to find the equation of the curve. That's what we quoted. The first part that has got to do with the differentiation is catered for in the other videos on differentiation. So we'll just try and look at the relevant parts again. So we are saying that the curve passes through the point A. Okay, the point A is given as 4, 6. So this is the point A. The question mentions that it is 4, 6, right? Then it says that it is also such that dy dx, the dy dx of it is going to give us 1 plus 2x raised to the power minus half. Okay, 1 plus 2x raised to the power minus half. And we are saying that a point P is moving along the curve in such a way that the x-coordinate of P is increased at a constant rate of 3 units. So that may not be relevant for us. Now, our focus is to find the equation of the curve. That's our part. How do you find the equation of the curve? Like we said, when you are given the dy dx, the anti-differentiation will produce the equation of y. So we'll just try and differentiate that, which means that our dy, which is 1 plus 2x raised to the power minus half dx, okay, we integrate this part like this. So our y takes, so the integral will take away the d. So we're going to have y, then we're going to deal with that. So this is going to give you x, okay, plus, then we add up, we add 1 to that. So we're going to have 2x minus half plus 1 all over minus half plus 1. Hope you are fine. Then we add our arbitrary constant c. So our y is going to give us x plus 2x raised to the power half all over half plus c. Any problem? So we are saying that this is happening at the point where a is 4, 1. What happens? You use this relation and put your slot in the values of a, the coordinates of a in there. That is, wherever you find x, you put 4 there. Wherever you find y, you put 6 there. When you're able to do that justice nicely, you should get your c. You should get your c looking at as minus 6. Hope you are fine. Your c should be looking like minus 6. All right. So your equation therefore is going to be y is equal to x plus 4 root x minus 6. So that is going to be the equation of the curve. And that brings us to the end of the II part of the question for question 9 QP 13. Question 10 QP 13 winter 2015. The function f is defined as f of x equals to 2x plus bracket x plus 1 to the power minus 2 for x greater than minus 1. The points A, minus half 3, and B, 1, 2 and a quarter, lie on the curve y is equal to 2x plus x plus 1 to the power minus 2 as shown in the diagram. I. Find, showing all necessary working, the area of the shaded region. Okay, so for question 10 QP 13, the third variant of 2017. This was the diagram that we were shown in there. I'll just try to reproduce it here, a bit of it there. So this area is a shaded region, and the point A, where the line cuts, they intersect the curve. So you're going to have that being minus 1 over 2, 3. Then that is 1, then 2 whole number, 1 over 4. And the equation of the curve is giving us 2x plus x plus 1 all raised to the power minus 2 for all values of x that are greater than negative 1. All right. So the II part, which is our focus, says that we should find, showing all necessary working, the area of the shaded region. The area of the shaded region. So how do we find that, the area of the shaded region? Now, you realize that, like we've always intimated and spoken about, that we've one area of the shaded region. Now, this is the shaded region that we are talking about. You will notice that from this part here, let's just try and extrapolate this down here. You will try and pull this one to down here. What do you see? You see that we get a trapezium. Is that not the case? We get a trapezium. So basically, if we want to find the area of the shaded region, it's like trying to find the area of the trapezium and taking away the area under the curve from it. Hope you are fine. You find the area of the trapezium like this. Find the area under the curve. Take it out of the area of the trapezium. The remainder is going to be the area of the shaded region, which we are being directed to find. All right, so how do we work that out? We find the area of the trapezium. We know for a trapezium. Okay, so for the area of a trapezium, we are going to have half the sum of the parallel sides times the height. So we're going to have half. What's going to be the parallel sides? So the parallel sides is going to be this sides. Those are the sides that are parallel. Okay, so we look at respectively the heights. Okay, so this is y. So the y point 2 over 4, that 1, 2 is 3. Hence, what are we going to get? You're going to get half, okay, half 3 plus 2 whole number 1 over 4. That's going to be the sum of the parallel sides. Then the height. So the height is going to be of that side, which means from this point to that point. And remember, this is negative half, and that is 1. So if we were to find that, what are you going to get? The height is going to be a subtraction. We're going to have times 1 and a half. Hope it makes sense. 1 and a half. Remember, 1 and a half, because if we were to do 1 minus half, you're going to have 1 plus half. And 1 plus half is 1 and a half. So that's what you're going to get. Now, if you work the area of the trapezium out, you should get 63 over 16 square units. Okay? So that's going to be the area of the trapezium. Now, we need to find the area under the curve, AB. That is bounded to the x-axis. So we integrate that side. So the area of the curve, what's going to be the integral? So we'll start from this to that. Hope you're fine. What's going to be our lower limit? I'm going to have minus half there, and our upper limit is going to give us 1. Okay? Then what do you have? 2x plus x plus 1 minus 2 dx. Now the problem tells us that we should show the necessary working, which means the focus is a bit on the integration aspect. We need to show how we did the integral. All right, so let's just go in there. If we integrate this is going to give you x squared, okay, because you add 1 and divide, plus linear factors. So what are you going to get? X plus 1 raised to the power minus 1 all over minus 1 times 1. Okay, then plus c. Oh, we don't need to bring c because it's a definite integral. All right, so 1 and minus half. Hope you are fine. That's what you get. Essentially, we are looking at x squared minus 1 over x plus 1. Okay, 1 minus half like this. That's what we want. All right, so when you do your simple substitution, which we know already, the area of that should give us 2.25 square units. 2.25 square units. Hence, when you want to find the area of the shaded portion, okay, the area of the shaded portion, what do you get? You are going to get the area of the trapezium, which is the 63 over 16 minus the 2.25. And guys, that should give you approximately 1.688 square units. So that is how you find the area of the shaded region for question 10, QP13. Find the area of the trapezium, which we found. Find the area under the curve, bounded from minus half to 1. And you do an integral. Remember the linear factors. What you need to do after you do that, it's a definite integral. You slot in there, the area gives you 2.25 square units. Since you want the area of the shaded portion, you subtract this from that. That's going to give you 1.688 square units for that. And that will bring you an end to the question 10, winter 2015.